Hello, and welcome to the Sleep with Science channel. Tonight, we will gently explore one of the most profound and influential discoveries in the history of science. Gravity is the quiet force that keeps your feet resting on the Earth. It guides the moon along its path through the night sky and determines the destiny of every star scattered across the universe. It is always present, yet most of the time, we hardly notice it. Gravity keeps our oceans from drifting away into space. It bends the light traveling from distant galaxies. It even changes the way time itself flows. Gravity is not merely the reason objects fall toward the ground. In many ways, it is the hidden architect shaping the entire cosmos. It molds planets into round worlds and gathers clouds of dust until they ignite as blazing stars. It choreographs the movement of celestial bodies and sends faint ripples through spacetime when black holes collide. Every orbit, every tide, every sunrise exists because of this quiet force. And yet, gravity is also one of the weakest and least understood forces known to science. Even today, researchers still do not fully know what gravity truly is. That uncertainty makes it one of the greatest mysteries in all of cosmology. If you enjoy these calm scientific journeys, feel free to like the video, subscribe to the channel, or leave a thought in the comments below. Your support helps other curious, sleepy minds discover this quiet corner of the internet. But for now, there is nothing you need to do except relax. Let your shoulders soften. Allow your breathing to slow down. And as your thoughts begin to unwind, join me as we begin this gentle journey through the universe. Let us begin. Gravity causes time itself to pass at slightly different speeds, meaning your feet age just a tiny bit faster than your head. Gravity does more than guide objects through space. It also changes the pace at which time moves. Deep within a strong gravitational field, time passes slightly more slowly. Higher up, where gravity becomes just a little weaker, time flows slightly faster. Because of this, the top of your head is technically aging just a little bit ahead of your feet. The difference is unimaginably small in everyday life, but with extremely precise clocks, it can be measured. This is not about the feeling of getting older. It is about the structure of the universe itself, allowing time to move at different rhythms depending on location. Gravity ties space and time together so closely that altering one inevitably influences the other. The moment we call now becomes something local rather than universal. Over very long periods, this effect accumulates. Time becomes almost like a landscape, with slopes and contours shaped partly by gravity itself. A black hole represents gravity pushed to such an extreme that even light cannot escape. There are places in the universe where gravity does not merely bend paths, it closes them entirely. Surrounding every black hole is a boundary known as the event horizon. Once anything crosses this boundary, every possible future path leads deeper inward. Even a photon, the fastest thing in existence, cannot escape. The event horizon is not a solid surface. Instead, it is a boundary in spacetime where escape becomes impossible. Even so, black holes can still reveal themselves. Gas and dust nearby can spiral inward, forming a glowing disk of incredibly hot material that shines brightly in X-rays. Stars that wander too close can be stretched apart by tidal forces, pulled into long streams of glowing debris. At the center lies not a cosmic vacuum cleaner, but an incredibly compact object whose mass curves spacetime dramatically. Perhaps the most mysterious aspect of a black hole is how simple it appears to be. In theory, it can be described by only a few properties. Yet despite that simplicity, it exerts a powerful influence over everything around it. The Moon remains in orbit around Earth because it is constantly falling but always missing the planet. The Moon is not floating motionless in space. Instead, it is moving sideways so quickly that its continual fall never quite catches Earth. Gravity pulls the Moon inward, while its sideways motion carries it forward. The result is a curved path that repeats month after month. If the Moon suddenly stopped moving sideways, it would not remain suspended. It would fall toward Earth. And if gravity somehow vanished, the Moon would not spiral outward. It would simply travel away in a straight line. An orbit is therefore a delicate balance between inward falling and forward motion. This is also why launching a spacecraft into orbit is not mainly about going upward. It is about reaching the correct sideways speed. Orbits can take many shapes. They can be low or high, circular or elongated into long ellipses. The Moon's steady path is a visible reminder of how gravity works across distances, shaping motion without physical contact and transforming falling into a stable celestial dance. Gravity slowly sculpts large planets into nearly perfect spheres. Small objects in space often have irregular shapes because their own gravity is too weak to reshape them. But once an object grows large enough, gravity begins to overpower the strength of rock and ice. High regions gradually slump downward. Low regions slowly fill in. Over millions of years, the entire body relaxes toward a spherical shape. This is why planets such as Earth appear round when viewed from space. Meanwhile, many asteroids resemble jagged potatoes. The process of becoming round is slow but relentless. Gravity acts like a patient sculptor, constantly pushing matter toward its lowest energy configuration. Inside young planets, heavier materials tend to sink, while lighter materials rise. This natural sorting creates layered interiors with dense metallic cores and lighter outer layers. It can also generate long-lasting internal heat. A sphere may appear perfect, but even planets are not perfectly smooth. Rotation can create a slight bulge around the equator. Collisions can leave scars across the surface. Still, the overall roundness of a planet is a signature that gravity has been quietly shaping it from the inside for billions of years. Tides occur because gravity stretches Earth's oceans rather than simply pulling them. If gravity pulled equally on every part of Earth, the oceans would move along with the planet without creating tides. But the Moon's gravity is slightly stronger on the side of Earth facing the Moon, and slightly weaker on the far side. This difference creates a stretching effect across the planet. Water, which flows easily, responds by forming two large bulges. As Earth rotates through these bulges, coastlines experience rising and falling sea levels. The Sun also contributes to this effect. Depending on its position relative to the Moon, it can strengthen or weaken the tidal pattern. Tides do more than move water. They transfer energy between Earth and the Moon. Over extremely long timescales, they can slowly alter rotations and orbits. Tides also shape coastal ecosystems, creating tidal zones where life exists between land and sea. The next time you look at a tide chart, you are really seeing a map of gravity translated into the rhythm of the ocean. You actually weigh slightly less at the equator because our planet is spinning. Weight is the force you feel from the ground pushing upward against your body. Near the equator, Earth's rotation is fastest. The surface of the planet moves more quickly there than anywhere else. This spinning motion creates a small outward effect that slightly reduces the force the ground must exert to keep you moving in a circular path with the planet. The difference is extremely small, but it can still be measured. It is also one reason Earth is not a perfect sphere. The equator bulges outward slightly because rotation partly counteracts gravity there more than it does near the poles. If Earth were spinning faster, this effect would grow stronger, and if it spun much faster still, rocks and oceans would begin struggling to remain attached to the planet. This is a vivid reminder that gravity is not the only influence shaping what you feel. Motion matters as well. Your weight depends on where you stand, how fast you are moving, and the shape of the world beneath your feet. Even the direction we call down carries a subtle regional accent. Gravitational waves are ripples in spacetime created by enormous cosmic collisions. When massive objects accelerate through space, they can disturb spacetime itself, sending waves outward across the universe. These waves do not move through space like ripples across water. Instead, they are ripples of space and time themselves. As one passes through an area, distances stretch slightly in one direction and compress in another. Then the pattern reverses. This stretching and squeezing carries energy away from the event that created it. The most powerful sources of gravitational waves involve incredibly dense objects. Black holes spiraling toward each other. Neutron stars colliding. Long before these objects finally merge, their orbit shrinks as energy radiates away through gravitational waves. The frequency of the waves rises steadily, producing what scientists often describe as a cosmic chirp. By the time these waves reach Earth, they are unimaginably faint, yet they still carry a precise signature of the masses and motion that produced them. For astronomers, gravitational waves represent an entirely new sense, a new way to observe the universe. They allow us to study violent events that may be hidden from telescopes by gas, dust, or darkness. Without gravity, stars would never ignite, and atoms might remain scattered across space. In the early universe, matter was spread thinly across vast regions. Gravity acted as the slow collector. It drew gas into slightly denser areas. Those denser regions then attracted even more gas. Gradually, enormous clouds formed. As a cloud collapses under its own gravity, it heats up. Eventually, the center becomes hot and dense enough for atomic nuclei to collide and fuse. A star is born. Gravity also helps atoms meet one another. Chemistry depends on collisions, proximity, and stable environments. Gravity provides those environments by forming planets and holding atmospheres and oceans in place. It turns a thin cosmic mist into structured worlds where complexity can develop. Without gravity, the universe would be a much lonelier place. There would be no long-lasting stars to power climates, no stable surfaces for life to grow upon. No slow cosmic assembly line turning simple ingredients into evolving systems. Isaac Newton famously connected the falling of an apple with the motion of the moon. The story is not really about fruit revealing physics. It is about recognizing a connection between two events that seemed unrelated: a falling apple in an orchard and a bright moon gliding across the night sky. Newton's brilliant step was to treat them as the same phenomenon acting at different distances. That idea allowed him to imagine a single rule that could explain both: why an apple accelerates downward and why the moon continues curving around Earth rather than drifting away. Once this link was established, motion stopped appearing as a collection of local quirks. Instead, it became part of a universal system. The same law could describe projectiles, tides, and planetary orbits. The remarkable part is that Newton worked with far less data than scientists possess today. The leap was conceptual. He invited humanity to believe that nature behaves consistently across both Earth and sky. That belief changed science forever. Albert Einstein later predicted that gravity could bend light, and solar eclipses provided the opportunity to test this extraordinary idea. Light seems weightless, which makes it feel impossible that gravity could affect it. But if space-time itself is curved, then even light must follow those curves. Einstein calculated how much starlight should shift as it passes near the sun. The challenge was observation. Normally, the sun's brightness hides nearby stars. But during a total solar eclipse, the moon blocks the sun's glare. For a few minutes, stars close to the sun become visible. In the early 20th century, scientific expeditions photographed those stars during an eclipse. Later, they compared the images with photographs taken when the sun was elsewhere in the sky. The stars had shifted exactly as Einstein predicted. The discovery electrified the scientific world. It was not merely a confirmation of a theory. It was proof that the structure of space itself could bend. The sun's gravity can also act like a natural magnifying glass. Gravity can function like a lens, even though no glass is involved. When a massive object lies between us and a distant source of light, it can bend and focus that light toward Earth. Astronomers call this phenomenon gravitational lensing. The result may appear as a brighter image, a distorted arc, or even multiple images of a distant galaxy. In rare cases where alignment is perfect, the light forms a ring around the massive object. This is known as an Einstein ring. What makes gravitational lensing so exciting is that it provides astronomers with a telescope created by nature itself. The universe supplies the lens. We simply supply the camera. These cosmic magnifiers allow scientists to see galaxies that would otherwise be too faint to detect. They can also reveal where hidden mass exists, including matter we cannot see directly. Whenever a distant object suddenly brightens in a peculiar way, it might be gravity briefly turning the universe into an optical instrument. Mercury's orbit slowly drifts in a way Newton's theory could not fully explain. Mercury travels around the Sun along an elliptical path. Over time, that ellipse slowly rotates. Most of this motion can be explained by the gravitational pull of other planets. But a small part of the drift remained unexplained. Astronomers searched for possible causes. Some even suggested an unseen planet closer to the Sun. But no such planet was found. The mystery persisted until Einstein developed his theory of general relativity. Near the Sun, space-time curvature becomes especially strong. Mercury, being the closest planet, feels that curvature more strongly than the others. When Einstein applied his equations, the missing shift appeared naturally. No hidden planet was required. A tiny discrepancy had opened a doorway to a deeper theory of gravity. Your phone's location works accurately because gravity changes how satellite clocks measure time. Global Positioning System satellites rely on incredibly precise timing. Your phone determines its position by comparing when signals arrive from multiple satellites. Even a small timing error would produce large location mistakes. However, satellites orbit high above Earth, where gravity is slightly weaker. In that weaker gravitational field, time flows a little faster. At the same time, satellites are moving very quickly. According to relativity, motion slows time slightly. Both effects must be accounted for. If engineers ignored them, GPS positions would drift rapidly and become useless. The remarkable thing is that relativity is not merely theoretical philosophy. It is practical infrastructure. Every navigation app quietly relies on corrections predicted by Einstein's theory. Your phone performs space-age physics calculations constantly without you ever noticing. Astronauts float in orbit not because gravity disappears, but because everything around them is falling together. From inside a space station, it may look as though gravity has vanished. But the station is still deep within Earth's gravitational field. The difference is that everything inside the station shares the same falling motion. The station itself, the astronauts, their tools, even the air. Because everything falls together, there is no solid floor pushing upward on the astronauts. Without that upward support force, the sensation of weight disappears. This is why water forms drifting spheres, and astronauts can move with the slightest push. The station travels sideways, fast enough that as it falls, Earth curves away beneath it. The fall never ends, so the floating never ends either. Gravity provides the stage. Speed keeps the performers from hitting the ground. Astronauts often grow slightly taller in orbit because gravity no longer compresses their spines. On Earth, gravity constantly presses down on the human body. The soft discs between vertebrae are slightly compressed. The natural curves of the spine are shaped by this steady pressure. In orbit, that compression disappears. The discs can rehydrate and expand slightly. As a result, astronauts may gain a small amount of height during a mission. This change can feel unusual at first. Some astronauts even experience back discomfort while their muscles adjust. The effect is temporary. Once they return to Earth, gravity resumes its gentle compression. Their height gradually returns to normal. What makes this fascinating is how quickly the body responds to new conditions. Height is not simply a number fixed forever. It is a living measurement influenced by fluids, tissues, and the forces acting upon them. Gravity keeps Earth's atmosphere from drifting slowly into space. Air may seem weightless, but every molecule has mass, and every molecule moves constantly. Near the top of the atmosphere, particles move rapidly and collide frequently. Occasionally, a collision sends a molecule upward fast enough to escape Earth's gravitational pull. Over billions of years, this process slowly removes some atmospheric gases. Earth retains most of its atmosphere because gravity is strong enough and temperatures are moderate. Temperature matters because heat increases molecular speed. Hotter atmospheres lose gas more easily. This is one reason small warm planets struggle to keep thick atmospheres, while larger planets can hold lighter gases. Earth's gravity allows clouds, weather, breathing air, and the protective layers that filter harmful radiation. Every breath you take reflects a delicate balance between chaotic molecular motion and the quiet grip of gravity. A balance that has lasted for billions of years. Gravity holds the oceans against Earth, yet it also shapes the overall level of the seas across the planet. Sea level is not simply the place where water meets land. Instead, it is a surface defined by gravity and by the rotation of Earth. Water naturally spreads across an invisible shape known as an equipotential surface. This means it flows until it can no longer move downhill. However, that surface is not perfectly smooth. It rises, dips, and tilts because mass inside Earth is not evenly distributed. Regions with extra mass pull water slightly toward them, raising the local sea level. Regions with less mass allow the surface to sit a little lower. Wind and ocean currents constantly move water across this surface, yet gravity always pulls it back toward equilibrium. This is why the phrase global sea level hides a surprising amount of complexity. The ocean is not resting inside a perfect bowl. Instead, it drapes itself across a living planet with a gravitational field that is slightly uneven. Every coastline on Earth measures that field day after day. Earth itself bulges around the equator because rotation partly counters gravity. Our planet spins once every day, and that motion changes what it means to be pulled downward. At the equator, Earth's surface travels fastest. Maintaining that circular path requires a constant inward pull. Gravity provides most of that pull, but the spinning motion reduces the effective force slightly. Over immense stretches of time, this balance influences the shape of the entire planet. Rock may feel solid and permanent, yet over geological time, it behaves almost like a very slow fluid. Given enough time, Earth relaxes into a shape that balances gravity with rotation. The result is an oblate spheroid, slightly wider around the equator than from pole to pole. This equatorial bulge affects satellite paths, navigation systems, and the way maps are calculated. It also reminds us that Earth is not a rigid object frozen in place. It is a rotating world, responding continuously to forces that never turn off. Mountains slightly weaken gravity because they increase the distance from Earth's center. Gravity becomes weaker the farther you move from the mass producing it. When you climb a mountain, you move slightly farther from the center of Earth. As a result, the gravitational pull becomes a tiny bit weaker. The difference is extremely small, but precise instruments can detect it. Interestingly, mountains themselves contain extra mass. Extra mass strengthens gravity. So two effects compete with one another. The increased distance weakens gravity. The additional rock strengthens it. In many places, the distance effect wins, meaning gravity at a mountain summit can be slightly lower than at nearby sea level. Mountains therefore become natural laboratories. By measuring these differences carefully, scientists can learn about the density of rocks deep within the crust. They can also study how mountain ranges are supported by structures hidden far underground. A peak is not simply a tall pile of rock. It hints at hidden architecture extending deep beneath the surface. Because gravity carries information through rock just as faithfully as it pulls you down a slope, dense underground rock strengthens gravity, and satellites can detect these differences. If we could see mass directly, Earth would appear patchy and textured. Some areas contain denser rocks or thicker crust. Others contain lighter materials or buried structures. These variations produce small bumps and dips in the gravitational field. Satellites passing overhead feel these changes. They speed up slightly when approaching regions of stronger gravity and slow down when leaving them. By measuring these subtle changes in motion, scientists can map gravity variations across the entire planet. Those maps reveal buried mountain roots, ancient volcanic provinces, and the scars of collisions that reshaped continents hundreds of millions of years ago. Gravity becomes a form of remote sensing. It works regardless of clouds, forests, or darkness. Gravity does not care about weather. It only responds to mass. That makes it one of the most powerful tools for studying Earth's hidden structure. Satellites can even track groundwater by detecting tiny shifts in gravity. Water has weight. When large quantities of groundwater move underground, the gravitational field changes slightly. During dry seasons, groundwater may be pumped away for agriculture. This reduces the total mass beneath a region. During wet seasons, aquifers refill and the mass increases again. Satellites designed to measure gravitational variations can detect these changes. They do not see individual wells or pipes. Instead, they measure the combined effect as if the land itself were slowly breathing water in and out. This technique has become a powerful tool for monitoring drought and water management. It can reveal where underground water reserves are shrinking. It can also show where conservation efforts are helping restore them. What makes this remarkable is the scale. Gravity allows scientists to measure invisible water supplies from space. The planet is constantly rearranging mass beneath our feet, and gravity quietly records the changes. Gravity mapping can also reveal ancient impact craters buried beneath Earth's surface. Some of the most dramatic structures on our planet are hidden. Sediment may fill ancient craters. Forests may cover circular mountain rings. Ice sheets may bury entire landscapes. But gravity can still detect them. Impact craters often leave distinctive gravitational patterns. The center may contain fractured rock with lower density. Around the edges, deeper layers may have been pushed upward, forming denser regions. By combining gravity maps with other geological data, scientists can identify ancient impact sites long after surface evidence has eroded away. Gravity, therefore, becomes a detective tool. It helps reconstruct chapters of Earth's history that appear erased from the surface. The ground beneath your feet contains stories older than any museum. Gravity helps translate those stories into patterns scientists can read. The moon also influences Earth's gravity through the motion of ocean tides. When the moon reshapes Earth's oceans, it moves enormous amounts of water around the planet. Water has mass, and moving mass changes gravity slightly. As tidal bulges travel across Earth, the distribution of mass shifts. Sensitive instruments can detect these minute changes in the gravitational field. These variations matter for extremely precise measurements of Earth's rotation and for accurate satellite tracking. It creates a beautiful feedback loop. The moon's gravity moves the oceans. The oceans change Earth's gravitational field. And that shifting field influences objects orbiting high above the planet. Earth is far more interconnected than it appears. The sea is not only water responding to wind, it is also part of Earth's gravitational fingerprint, continuously reshaped by the moon. Falling is universal, but weight depends on what supports you. Mass measures how much matter you contain. Weight measures how strongly something must push upward to support you against gravity. The difference becomes clearer in unusual situations. When you stand on a scale, the scale compresses slightly under the force of your body. That compression measures the support force holding you up. If you stand in an elevator that accelerates upward, the scale reading increases. Your body requires a larger upward force to match the motion. If the elevator accelerates downward, the reading decreases. In free fall, the scale reading can approach 0. Yet gravity has not disappeared. You are simply no longer being supported. This is why astronauts feel weightless in orbit. Weight is not a permanent property of your body. It is a conversation between you and whatever is pushing upward beneath you. Once you notice that, everyday sensations become clues about physics. Even the strange feeling in your stomach during an elevator ride is gravity and motion speaking through your nervous system. On Mars, you could jump higher because gravity is weaker than on Earth. Mars has much less mass than our planet. Its surface gravity is therefore weaker. The same push from your legs would launch you higher, and keep you in the air longer. Walking would feel different. Your steps would stretch out. Falls would last longer, giving you extra time to react. Sports would change dramatically. A simple jump might turn into a graceful arc. A thrown object could travel much farther with the same effort. Yet Mars would not feel like the Moon. Its gravity is still strong enough to provide a clear sense of down. Objects would still fall reliably. Gravity shapes movement like a rhythm. Change that rhythm, and the choreography of everyday actions changes with it. Mars would feel familiar, yet strangely dreamlike, as though every motion carried just a little more pause between steps. On Jupiter, you would weigh much more, if there were solid ground to stand on. Jupiter's gravity at the level of its cloud tops is stronger than Earth's gravity. If you somehow stood there, your body would feel noticeably heavier. Simple movements would demand more effort. Standing up would feel like exercise. Even breathing might feel harder, because the muscles in your chest would have to lift and lower more weight with every breath. But there is a deeper twist to this thought experiment. Jupiter does not actually have a solid surface like Earth. Instead, it is made mostly of hydrogen and helium gases that grow denser and stranger the deeper you travel. As you descend, pressure rises enormously. Winds roar at tremendous speeds. Temperatures increase. Long before anything like solid ground appeared, the environment would become completely hostile. So imagining yourself weighing something on Jupiter is both vivid and impossible at the same time. Jupiter teaches two lessons at once. Gravity can be stronger than Earth's, and yet the world itself may still be unwalkable. It reminds us that the word planet does not always mean a place with land beneath your feet. A neutron star compresses the mass of a sun into an object no larger than a city. When a massive star reaches the end of its life, its core can collapse catastrophically. The collapse is so violent that electrons and protons are forced together, merging into neutrons. What remains is a neutron star, an object perhaps 20 kilometers across, yet containing more mass than our entire sun. The density is almost unimaginable. Matter is pushed far beyond familiar states. The gravitational pull at the surface becomes extraordinary. Magnetic fields around these stars can be billions of times stronger than those around Earth. Many neutron stars rotate incredibly fast. Some spin dozens or even hundreds of times every second. As they spin, beams of radiation sweep through space like the light from a cosmic lighthouse. When those beams pass across Earth, we detect regular pulses. For this reason, these objects are known as pulsars. What makes neutron stars so remarkable is the contrast between their size and their influence. On a cosmic scale, they are tiny, yet they can bend space-time, accelerate particles, and serve as some of the most precise natural clocks in the universe. Neutron stars are what happens when gravity pushes matter to the very edge of what physics can describe. Near a neutron star, even a small pebble could strike with enormous force. The gravity near the surface of a neutron star is so intense that objects accelerate dramatically over very short distances. Even a small fall becomes extremely violent. When something falls, Gravity converts gravitational potential energy into motion. That motion carries energy. Near Earth, the conversion is modest. Near a neutron star, the conversion is extreme. A pebble dropped from your hand there would strike with the energy of a powerful explosion. The pebble itself has not changed. The environment has. Gravity has given it enormous acceleration. The same powerful gravity also produces extreme tidal forces. The difference in gravitational pull between the near side of an object and its far side becomes enormous. Anything extended, including a human body, would experience intense stretching forces. Near a neutron star, everyday intuition quickly breaks down. It becomes a place where gravity transforms even small objects into powerful projectiles. Gravity weakens rapidly with distance, much faster than our intuition often expects. If you double your distance from a mass, its gravitational pull does not simply become half as strong. Instead, it becomes only 1/4 as strong. This steep decline explains why objects can dominate their surroundings nearby, yet become nearly irrelevant from far away. It also explains why gravity never truly turns off in space. Astronauts in orbit still experience strong gravity because they remain relatively close to Earth. What changes is not the strength of gravity itself, but how little it varies across their bodies and how fast they are moving sideways. This rapid weakening of gravity also shapes the architecture of solar systems. Planets dominate their immediate surroundings, but the Sun still governs the entire system. Far beyond the planets, even the Sun's influence grows faint. Passing stars can sometimes nudge distant comets into new paths. Gravity reaches everywhere, yet its strength is always edited by distance. Distance is a ruthless filter. Gravity can pull comets back toward the Sun, even after centuries in deep space. Some comets spend most of their lives far beyond the familiar planets. They drift through darkness for hundreds, sometimes thousands of years. Then, guided by gravity alone, they return to the inner solar system. Their paths are enormous, elongated loops. No engine guides them, only the quiet pull of the Sun. As a comet approaches the Sun, sunlight warms its frozen surface. Ice begins turning directly into gas. Dust and gas escape, forming a glowing coma and a long, luminous tail. After passing near the Sun, the comet swings outward again. Gradually, it fades into darkness once more. Its return may not happen again for generations. People may live entire lifetimes without seeing the same comet twice. Yet gravity keeps the schedule. The solar system remembers, even when the timetable stretches beyond human history. Jupiter's gravity gathers asteroids into stable Trojan swarms. Jupiter is the largest planet in our solar system. Its immense gravity dominates its orbital region. But instead of simply scattering everything nearby, it also creates pockets of stability. Along Jupiter's orbit lie special regions called Lagrange points. In these regions, the gravitational influence of Jupiter and the Sun combine with orbital motion in a balanced way. Asteroids trapped in these zones are called Trojans. They travel in two large swarms. One group leads Jupiter along its orbit. The other follows behind. These asteroids are not arranged neatly. They drift and weave within their regions. Yet the overall pattern remains stable for millions of years. Studying Trojan asteroids helps scientists understand the early solar system. Many of them may be leftover fragments from the era when planets first formed. Jupiter can be both a threat and a refuge. Its gravity can scatter objects violently, but it can also create safe gravitational harbors where asteroids remain protected for ages. Saturn's rings exist partly because gravity can tear moons apart. Saturn's rings appear delicate and graceful, yet their origin may involve destructive forces. When a moon travels too close to a massive planet, tidal forces become extremely strong. The side of the moon nearest the planet feels a stronger gravitational pull than the far side. If this difference becomes too great, the moon can be torn apart. Instead of remaining intact, the fragments spread into orbit around the planet. Collisions between fragments grind them into smaller pieces. Over time, a vast disk of icy particles forms. This is likely how Saturn's rings began. Each tiny particle travels in its own orbit, yet together they form an enormous, shimmering structure. Nearby moons shape the rings further. Their gravity creates waves, gaps, and sharp edges. Saturn's rings are therefore both a product of creation and destruction. The same gravity that organizes them may also have destroyed the moon that created them. There is a distance around a planet known as the Roche limit, a boundary where objects can begin to break apart under tidal gravity. This boundary is not a sharp cliff in space. It is a threshold that depends on several factors, including the density of the object, its internal strength, and what materials it is made from. A loosely bound object made of rubble may begin to break apart farther away than a solid body made of stronger rock. Inside this region, the planet's gravity pulls more strongly on the near side of the object than on the far side. This uneven pull stretches the object. If the material cannot resist that stretching force, fractures appear. Eventually, the object can break into fragments. Understanding the Roche limit helps explain why rings form around certain planets and why moons tend to orbit outside particular distances. It also helps scientists understand what may happen during close encounters between objects in space. Sometimes, a comet or asteroid passing too close to a large planet will stretch and break apart. The fragments may continue along similar paths, forming a long chain of objects trailing through space. Gravity, in this situation, becomes both a sculptor and a breaker. It shapes structures, but it also sets the point where those structures fail. Earth's gravity slowly pushes the moon farther away over time. Earth and the moon are connected through tides, but tides are not perfectly efficient. As Earth rotates, the tidal bulges created in the oceans do not line up exactly with the moon. Because the planet spins, those bulges are carried slightly ahead of the moon's position. This offset creates a small gravitational tug. The bulge pulls forward on the moon as it orbits. That tiny push increases the moon's orbital energy. As a result, the moon gradually moves into a slightly higher orbit. This process is incredibly slow. The moon drifts away from Earth by only a few centimeters each year. Yet over millions and billions of years, the change becomes significant. The process also leaves clues in ancient rocks and fossils. Certain layered sediments and growth patterns in ancient organisms record how long Earth's days were in the distant past. Long ago, Earth rotated faster, days were shorter. The moon's slow retreat is not dramatic. It is a patient migration measured in millimeters each year, driven by the everyday movement of ocean water. The moon's gravity also slows Earth's rotation, gradually lengthening the length of a day. The same tidal interaction that pushes the moon outward also acts like a gentle brake on Earth's spin. Tides create friction. Ocean water moves across the seafloor. Currents stir and swirl. Energy is lost as heat. That lost energy comes from Earth's rotational motion. Over immense periods of time, the planet's spin slows. The result is that days slowly grow longer. The change is far too small to notice within a human lifetime. But over geological timescales, it becomes measurable. Hundreds of millions of years ago, Earth spun faster. The rhythm of daylight across the planet was different. As the rotation slows, patterns in climate and ocean circulation can gradually adjust. Life evolves alongside those slow changes. What makes this fascinating is the partnership. A distant object in the sky, the moon, can influence the length of your day without ever touching Earth. Gravity alone is enough. Gravity can sometimes capture wandering objects and turn them into moons. In space, most close encounters are brief. An object approaches a planet. Its path bends under gravity. Then it moves away again. But occasionally, something different happens. If energy is removed from the object's motion, it may become trapped. One way this can occur is through a three-body interaction. If an object passes near a planet that already has moons or debris around it, gravitational forces may redistribute energy between them. One body may gain energy and escape. Another may lose energy and become captured. Captured moons often follow unusual orbits. Some travel in retrograde directions, moving opposite the planet's rotation. Others orbit at steep angles. These unusual paths are clues to their dramatic origins. Each captured moon represents a story of near misses and lucky gravitational exchanges. Gravity transforms a fleeting encounter into a permanent relationship. Venus spins in a strange way, influenced partly by gravity over vast periods of time. Venus rotates very slowly compared to most planets. Even more unusual, it rotates in the opposite direction of many other planets. If you stood on the surface of Venus, the sun would appear to rise in the west and set in the east. Scientists are still studying why this happened. One possible factor involves tidal interactions between Venus and the sun. Over long periods, the sun's gravity can apply torques that influence the spin of nearby planets. Venus also has an extremely dense atmosphere. Moving air carries momentum. Over time, that atmosphere can interact with the surface, subtly affecting the planet's rotation. These effects operate over millions and billions of years. Planetary rotation is not always fixed from the moment a planet forms. Gravity, tides, and atmospheric motion can slowly reshape it. When you see Venus shining as the evening star, you're looking at a world whose sense of time moves very differently from our own. Small gravitational nudges can make planetary orbits behave chaotically over millions of years. At first glance, the solar system appears orderly. Planets follow regular paths around the sun. But beneath that order lies complexity. Every planet pulls on every other planet. Most of the time, those tiny gravitational tugs cancel out. But over very long times, small influences can accumulate. In mathematics, this behavior is called chaos. Chaos does not mean sudden destruction. Instead, it means that extremely small differences in starting conditions can grow over time. Eventually, precise predictions become impossible. An orbit may drift from one pattern of influence to another. Resonances between planets may appear and disappear. Orbital shapes can slowly stretch or shrink. The solar system, therefore, contains both order and unpredictability. Gravity creates elegant repeating patterns, yet it also seeds complexity that no perfect clockwork can fully control. The solar system is both a poem of rhythm and a laboratory of chaos. Gravity is the weakest fundamental force, yet it dominates the largest structures in the universe. At the scale of atoms, gravity is extremely weak. Electromagnetic forces hold atoms together. They govern chemistry and the structure of materials. Compared to those forces, gravity is almost negligible. But gravity has a crucial advantage. It always attracts, and it always adds together. Electric charges can cancel each other out. Positive and negative charges neutralize. Mass, however, has no opposite. There is no negative mass that cancels ordinary matter. So when large amounts of matter gather, gravity grows steadily stronger. On the scale of planets, stars, and galaxies, gravity becomes the dominant force. It shapes the collapse of gas clouds. It controls the motion of stellar systems. It determines the structure of the universe itself. Gravity does not act loudly. It works slowly, patiently, over immense distances and enormous stretches of time. Gravity is the quiet accountant of the cosmos, endlessly adding up every piece of matter and translating those totals into motion. Galaxies form because gravity gathers matter into enormous rotating cities of stars. In the early universe, matter was not distributed perfectly evenly. There were tiny differences in density, regions that contained just a little more material than their surroundings. Gravity amplified these differences. Areas with slightly more mass pulled in additional matter. As they grew denser, their gravitational pull increased even further, drawing in still more gas. Over time, enormous clouds formed and began to collapse. As gas fell inward, it heated and compressed. Inside these clouds, fragments formed where stars could ignite. At the same time, angular momentum, the tendency of rotating systems to keep rotating, shaped the structure of these growing systems. Rather than collapsing into simple spheres, much of the material spread into rotating disks. Within these disks, spiral patterns could emerge like slowly moving waves. A spiral galaxy therefore becomes something like a vast cosmic city. Billions of stars orbit together within a shared gravitational home. Between them lie clouds of gas and dust, and surrounding everything is an even larger structure of unseen mass that deepens the gravitational well. Within spiral arms, new stars are born. In quieter regions, ancient stars drift slowly through space. Gravity is the glue that holds this enormous system together, but it is also the storyteller guiding its evolution. Gravity gathers material, compresses it into stars, and binds the galaxy together for billions of years. When you look at the Milky Way stretching across a clear night sky, you are seeing the glowing trace of that long process of gathering, a river of stars shaped by gravity. Galaxy clusters form when gravity binds entire galaxies together across immense distances. A single galaxy is already unimaginably vast. Yet galaxies themselves are not isolated. They gather into even larger families known as galaxy clusters. Within a cluster, hundreds or sometimes thousands of galaxies orbit a shared center of mass. The space between them is not empty. It contains enormous reservoirs of extremely hot gas. This gas can reach temperatures of millions of degrees and shines brightly in X-rays. Surrounding everything is an even larger structure of invisible matter helping to hold the cluster together. Within clusters, galaxies interact. Close encounters stretch their shapes. Gas can be stripped away, altering their ability to form new stars. Clusters also mark the places where the universe has had enough time to gather matter on the largest scales. Their gravity is strong enough to bend light from objects behind them, producing gravitational lensing effects. By studying clusters, astronomers learn how cosmic structures grow and evolve. Thinking about a galaxy cluster is like zooming out from a single city to an entire continent. Gravity still organizes everything, but now the map spans millions of light years, and the timescales stretch far beyond human imagination. Dark matter is inferred because gravity appears stronger than visible matter alone can explain. When astronomers measure how quickly stars orbit inside galaxies, they discover a mystery. The outer stars move faster than expected. If only visible stars and gas were present, gravity would not be strong enough to hold those fast-moving stars in orbit. Yet they remain bound to the galaxy. The same puzzle appears when studying galaxy clusters. Galaxies inside clusters move too rapidly to be held together by the gravity of visible matter alone. Something unseen must be adding extra gravitational pull. Scientists call this missing component dark matter. It is called dark not because it is mysterious in a dramatic sense, but because it does not emit or absorb light in the usual way. We detect it indirectly through its gravitational influence, through the motions of stars, through the bending of light, through the growth of cosmic structures. Dark matter has not yet been identified as a specific particle, but the evidence for additional unseen mass appears across many independent observations. Gravity, therefore, becomes a messenger. It tells us that the universe contains far more than what we can directly observe. The galaxies we see are like lanterns hung along a vast, invisible framework. Gravity lets us feel that framework even when we cannot see it. And that hidden structure is one of the great mysteries still waiting to be solved. Gravity can trap enormous halos of hot gas around galaxies and clusters. In galaxy groups and clusters, gravity holds onto vast reservoirs of gas that would otherwise drift away into intergalactic space. As this gas falls inward, collisions between particles heated to extreme temperatures. At millions of degrees, the gas emits powerful X-ray radiation. These halos are not decorative features. They contain a large fraction of the ordinary matter in these systems. The hot gas behaves almost like weather on a cosmic scale. Galaxies moving through it can lose their own gas through friction and pressure. When that happens, star formation inside those galaxies can slow or even stop. Meanwhile, cooling regions of the gas can flow inward toward central galaxies. There, the material may feed enormous black holes at their centers. In this sense, the halo acts like an atmosphere for the cluster itself. It fills the space between galaxies with something dynamic and influential. When we picture a galaxy cluster, it is easy to imagine scattered islands of stars floating in emptiness. But in reality, they are immersed in a vast invisible ocean of extremely hot gas, held in place by gravity. The cosmic web exists because gravity pulls matter into enormous filaments. On the largest scales imaginable, the universe resembles a vast network. Matter is arranged in long filaments stretching across hundreds of millions of light years. Between these filaments lie enormous empty regions called voids. At the intersections of the filaments sit dense nodes where galaxy clusters form. This structure is called the cosmic web. It grew from tiny irregularities present shortly after the Big Bang. Regions that were slightly denser than average began pulling in surrounding matter. As they grew, they drew material along preferred directions. Over billions of years, the universe developed a web-like architecture. Galaxies tend to form along the filaments. Clusters appear where filaments intersect. The web is not made of threads you could touch. It is a map of where matter has gathered under gravity's influence. Gas flows along these filaments, feeding galaxies and clusters. The cosmic web therefore acts like the skeleton of the universe. When we observe deep images of space, we see countless points of light. But gravity has woven them into an enormous structure stretching across billions of light years. Gravity can cause collapsing stars to spin faster, much like a skater pulling in their arms. When a star's core contracts, its rotation rate can increase dramatically. This happens because angular momentum must be conserved. If mass moves closer to the axis of rotation, the spin must speed up. Figure skaters demonstrate this principle clearly. When they pull their arms inward, they spin faster. Stars behave in a similar way. As their cores collapse, their rotation accelerates. This increased rotation can shape magnetic fields. It can channel explosions in specific directions. It can influence the type of compact object left behind after a star dies. In some cases, rapid rotation helps create powerful jets of matter and energy that shoot outward from the star's core. The principle itself is simple, yet it helps explain some of the most dramatic events in the universe. Gravity compresses matter. Rotation responds. And that response can turn the final moments of a star's life into spectacular cosmic displays. Supernova explosions can create the conditions for new stars and planetary systems. A supernova appears to be pure destruction. A star explodes with tremendous energy, blasting its outer layers into space. But after the light fades, gravity still remains. The expanding cloud of debris contains heavy elements forged inside the star. As the cloud moves through space, it can compress nearby gas. Those compressed regions may collapse under gravity. Eventually, they form new stars. Around those stars, planets can begin to assemble. In this way, gravity transforms an ending into a beginning. The remnants of the original star may become a neutron star or black hole. These objects continue influencing their surroundings through gravity and radiation. A supernova itself lasts only days or months, but its consequences can shape star formation for millions of years. Gravity is the thread connecting these chapters. It gathers material to form the star. It holds the star together during its lifetime, and after the explosion, gravity gathers the scattered fragments once more. The universe rebuilds, again and again. Gravity ignites nuclear fusion inside stars by compressing hydrogen until temperatures rise high enough for atomic nuclei to collide. A star begins its life as a cold cloud of gas drifting quietly through space. At first, the cloud is far too thin and diffuse to shine, but gravity slowly gathers the gas inward. As the material falls toward the center, it accelerates. Particles collide more frequently. Each collision converts motion into heat. Gradually, the central region becomes hotter and denser. Eventually, the conditions become extreme enough that hydrogen nuclei begin overcoming their natural electrical repulsion. When that happens, fusion begins. Hydrogen nuclei combine to form helium, releasing enormous energy. That energy pushes outward, balancing the inward pull of gravity. A star is therefore a delicate equilibrium. Gravity squeezes inward, hot gas and radiation push outward. When these forces balance, the star shines steadily for millions or even billions of years. The ignition of a star is not a sudden spark like lighting a match. It is a threshold reached through relentless compression. Gravity patiently climbs toward the conditions where nuclear reactions become possible. Without gravity, gas clouds would simply remain cold and scattered. With gravity, the universe lights up. Invisible clouds become brilliant suns, capable of warming planets and illuminating night skies. Brown dwarfs exist because gravity sometimes falls just short of creating a true star. Between planets and stars lies a fascinating class of objects called brown dwarfs. These objects form the same way stars do. A cloud of gas collapses under gravity. The material heats as it compresses. However, brown dwarfs never quite reach the conditions needed for sustained hydrogen fusion. Their mass is simply too small. Gravity cannot compress their cores strongly enough to ignite the same reactions that power true stars. Some brown dwarfs can fuse a limited fuel, such as deuterium, for a short time, but they cannot maintain long-term hydrogen fusion. Instead, they glow faintly from leftover heat generated during their formation. Over time, they slowly cool and fade. They are sometimes called failed stars, though the term is misleading. Brown dwarfs occupy their own unique category. They bridge the gap between planets and stars. Some even have clouds and weather systems in their atmospheres. Many likely host their own planetary companions. Their existence reveals something important about gravity. A small change in mass can completely alter the fate of an object. A little more mass and gravity ignites a star. A little less and the object becomes something planet-like. Brown dwarfs live precisely on that boundary. The Sun's gravity determines the orbital speed of every planet in the solar system. Planets closer to the Sun move much faster along their orbits. Those farther away travel more slowly. This pattern arises from a simple but powerful principle. To remain in orbit, an object must move sideways fast enough to avoid falling inward. Close to the Sun, gravity is stronger. A planet must move quickly to keep curving around the Sun instead of plunging toward it. Mercury therefore races around the Sun at tremendous speed. Neptune, far away in the cold outer system, can move more slowly. The gravitational pull there is weaker. This relationship transforms the solar system into something like a speed map. Distance from the Sun sets the pace. Inner planets complete their orbits quickly. Outer planets take many years to circle the Sun. Even though every planet follows the same gravitational rule, the results vary dramatically with distance. The Sun does not drag the planets around like objects on a string. Instead, it shapes the paths they naturally follow. And speed becomes the price each planet pays to remain in orbit. Earth and the Moon orbit a shared center of gravity hidden inside Earth. It is common to say that the Moon orbits Earth. But in a more precise sense, both bodies orbit a shared point called the barycenter. This point lies along the line between Earth and the Moon. Because Earth is much more massive, the barycenter sits inside Earth itself, though not exactly at its center. As the Moon moves along its orbit, Earth performs a small wobble around this shared point. The motion is subtle but real. The planet itself participates in the celestial dance. This wobble affects precise calculations used for tracking spacecraft and satellites. It also influences how scientists model Earth's motion through space. Gravity is always mutual. Earth pulls on the Moon. The Moon pulls on Earth with equal strength. The difference lies in how each body responds. Earth's enormous mass means its motion is smaller, but it still moves. Even the ground beneath your feet participates in this slow gravitational waltz. The Sun itself wobbles slightly because orbiting planets tug on it. And astronomers use this motion to discover distant worlds. A star with planets is not perfectly stationary. As planets orbit, their gravity pulls gently on the star. The star shifts back and forth in response. From very far away, astronomers can detect this motion. They measure tiny changes in the star's velocity along our line of sight. The star's light shifts slightly toward red or blue as it moves toward or away from us. This repeating pattern reveals the presence of unseen planets. The technique is known as the radial velocity method. It has discovered many exoplanets that never pass directly in front of their stars. Large planets are easier to detect because their gravitational pull is stronger. The method feels almost magical. Astronomers cannot see the planet directly. Instead, they watch the star move slightly, as if something invisible were tugging on it. Each wobble is a gravitational whisper saying, "Something is here. Something with mass is orbiting." Binary star systems allow scientists to measure stellar masses directly. When two stars orbit each other, gravity transforms them into a natural laboratory. By observing the size of the orbit and how long the stars take to complete one revolution, astronomers can determine the combined mass of the pair. If they can also measure how much each star moves, they can calculate the mass of each star individually. This information is incredibly important. Mass determines almost everything about a star's life: its brightness, its lifespan, the type of explosion or remnant it will eventually produce. Binary stars therefore serve as calibration tools for stellar physics. Some binary systems pass in front of each other from our perspective. These eclipsing binaries allow scientists to measure stellar sizes with extraordinary precision. Others reveal themselves through shifts in their spectral lines as the stars move. Gravity writes the signature. The orbit becomes the handwriting. And from that handwriting, astronomers read the physical properties of distant stars. Even though humans can never touch distant stars, spacecraft can gain speed by using gravity instead of burning additional fuel. This technique is known as a gravitational assist, or sometimes a gravity slingshot. When a spacecraft approaches a moving planet, it enters the planet's gravitational field and begins to curve around it. If the spacecraft approaches in the correct direction, usually passing behind the planet relative to the planet's motion around the Sun, the interaction can increase the spacecraft's speed. The planet's gravity bends the spacecraft's path, but because the planet itself is moving, the spacecraft leaves the encounter carrying away a small portion of the planet's orbital momentum. To the spacecraft, the maneuver appears like a powerful boost. To the planet, the change is extremely tiny and completely unnoticeable. Yet for the spacecraft, the gain in speed can be enormous. Many deep space missions rely on this technique. The Voyager probes, for example, used multiple gravitational assists from the outer planets to reach the edge of the solar system. Gravity assists do not create energy from nothing. They simply borrow energy from motion that already exists. But the effect feels almost magical. Space travel becomes less about carrying huge amounts of fuel and more about timing and choreography. Arrive at the right place, at the right moment, and gravity itself can do the work. Sometimes the most valuable part of a gravity assist is not speed, but direction. A planet's gravity can bend a spacecraft's trajectory dramatically. In some cases, engineers use a flyby primarily to redirect a spacecraft toward a new destination. The maneuver is similar to the motion of a billiard ball striking the cushion of a pool table. The ball changes direction after the collision. In space, gravity performs the role of the cushion. By choosing the correct approach angle and altitude, mission planners can reshape a spacecraft's path through the solar system. One flyby might tilt the spacecraft's orbital plane. Another might send it inward toward the Sun. Another might fling it outward toward distant planets. Each maneuver is planned years in advance. The spacecraft travels for months or years before reaching the exact location needed for the maneuver. The moment itself lasts only hours. Yet the effect can change the entire journey. In this way, the planets become tools. Gravity becomes a steering wheel guiding exploration across enormous distances. There are special regions in space where gravity and motion combine to create stable balance points. These locations are called Lagrange points. In a system with two large bodies, such as the Earth and the Sun, there are 5 points where the gravitational pulls and orbital motion balance in a special way. A small object placed near one of these points can remain in roughly the same configuration relative to the larger bodies. Some Lagrange points are stable. Objects drifting near them tend to remain nearby, like marbles resting inside a shallow bowl. Other points are unstable and require occasional adjustments to maintain position. Even so, these regions are incredibly useful. They are not physical places marked by surfaces. They are invisible coordinates defined purely by gravity and geometry. Dust and small asteroids can accumulate naturally at certain Lagrange points. Space missions can also use them as observation platforms. These points reveal something subtle about gravity. Gravity is not only a force pulling objects inward, it also creates pockets of balance within motion, places where the cosmic tug-of-war briefly pauses. Some space telescopes operate near Lagrange points because the environment there is unusually stable. A telescope in space needs darkness, stable temperatures, and an unobstructed view of the sky. Certain Lagrange point orbits provide exactly these conditions. For example, near the Earth-Sun system's second Lagrange point, called L2, a telescope can keep both Earth and the Sun on the same side of the spacecraft. This arrangement allows engineers to place a sun shield that blocks heat and light from both bodies. With those bright sources clustered together, the telescope can remain extremely cold and stable. This stability is essential for sensitive instruments. Even tiny temperature changes can slightly distort a telescope's mirrors. Those distortions could blur images. At L2, a telescope can also communicate reliably with Earth while scanning the sky with minimal interruptions. The spacecraft does not sit perfectly still. Instead, it follows a looping path around the balance point. But the region remains calm compared to many other orbits. Rather than forcing the telescope to fight disturbances, mission designers place it where gravity naturally reduces them. In that calm environment, the telescope can see farther into the universe. Gravity can also lock moons and planets into repeating orbital rhythms called resonances. When two orbiting bodies have periods that form a simple ratio, their gravitational interactions repeat in a regular pattern. For example, one object might orbit exactly twice for every orbit of another, or 3 times for every 2. Each time the bodies align in the same configuration, gravity applies a small, repeated tug. Individually, each tug is tiny, but because the timing repeats perfectly, the influence builds over time. This effect is called orbital resonance. Some resonances stabilize systems. They keep moons spaced in predictable patterns. Other resonances can stretch orbits into more elongated shapes. Resonances also help explain gaps in planetary rings and patterns in asteroid belts. Gravity in these cases acts almost like a metronome. The rhythm matters as much as the strength. A small push delivered at exactly the right moment, again and again, can shape entire planetary systems. Hidden musical relationships exist among many celestial orbits, and gravity is the composer that rewards simple ratios with long-lasting harmony. One of the most dramatic examples of tidal heating occurs on Jupiter's moon Io. Io should have cooled long ago. Given its size, its internal heat from formation should have faded billions of years in the past. Yet Io remains the most volcanically active body in the solar system. Its surface is constantly reshaped by lava lakes and towering volcanic plumes. The reason lies in gravity. Io travels in a slightly elliptical orbit around Jupiter. As it moves closer to and farther from the giant planet, Jupiter's gravitational pull changes slightly. That difference stretches and squeezes Io repeatedly. The constant flexing generates friction inside the moon's interior. That friction becomes heat. The process is similar to bending a paperclip back and forth until it becomes warm. But on Io, the scale is enormous. Gravity converts orbital energy into internal heat. The result is a world kept molten by its giant neighbor. Jupiter never touches Io, yet its gravity makes the moon erupt endlessly. Tidal heating may also allow distant icy moons to hide liquid oceans far from the warmth of the sun. Heat in the universe does not always come from sunlight. Some moons are warmed by gravity itself. If a moon's orbit remains slightly non-circular, the gravitational pull from its parent planet changes throughout the orbit. This repeated deformation generates internal heat. That heat can melt ice deep beneath the surface. Even in the cold outer regions of the solar system, subsurface oceans may remain liquid. These hidden oceans could exist beneath thick shells of ice. Some moons may even produce cryovolcanoes, eruptions of water and ice instead of molten rock. Tidal heating expands the range of places where active geology might occur. It also expands the possible habitats where life could exist. A world does not need to orbit close to a star to have energy and chemical activity. Gravity itself can provide the heat. A distant moon, wrapped in darkness, might still hide a warm ocean beneath its frozen crust. Gravity can also create long-lasting orbital resonances that protect entire regions of the solar system from chaos. In some cases, resonances act like invisible fences. They keep objects away from certain areas of space. In other cases, they create stable pathways where objects can remain for millions or even billions of years. The asteroid belt between Mars and Jupiter contains many such patterns. Some regions are nearly empty. These gaps appear because Jupiter's gravity repeatedly disturbs objects that try to orbit there. Every time an asteroid completes its orbit, Jupiter returns to the same relative position and delivers another gravitational nudge. Over time, those nudges push the asteroid into a new orbit. These empty regions are called Kirkwood gaps. Yet other resonances create the opposite effect. They stabilize objects in predictable orbits. Gravity therefore acts like a cosmic traffic system. Some lanes are safe, others are unstable. Objects drift until they find paths where repeated gravitational influences either cancel out or reinforce stability. The architecture of the solar system is partly written by these repeating rhythms. A rhythm too strong can eject an asteroid. A rhythm perfectly balanced can preserve one for billions of years. Gravity organizes motion not only through force, but through timing. Comets can break apart when they pass too close to a massive planet. When a fragile comet approaches a giant planet like Jupiter, tidal forces can become enormous. The side of the comet closer to the planet experiences a stronger pull than the far side. If the difference becomes large enough, the comet begins to stretch. Cracks form. Eventually, the object may break into multiple fragments. Instead of one comet, a long chain of pieces continues along a similar path. Astronomers witnessed this dramatically in 1994 when comet Shoemaker-Levy 9 collided with Jupiter. Before the impact, Jupiter's tidal forces had already torn the comet apart. More than 20 fragments followed one another like beads on a string. One by one, they plunged into Jupiter's atmosphere. Each impact produced enormous explosions visible from Earth. The event revealed something remarkable. Even delicate icy bodies drifting through space are subject to powerful gravitational sculpting. Gravity can break things apart just as easily as it can hold them together. The same force that builds planets can also dismantle them. Some stars orbit the supermassive black hole at the center of our galaxy at astonishing speeds. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius A star. Its mass is millions of times greater than the mass of our Sun. Near this enormous concentration of gravity, stars follow extremely fast and tightly curved orbits. Astronomers have tracked several of these stars for decades. One star, known as S2, completes an orbit in only about 16 years. During its closest approach, it races through space at thousands of kilometers per second. These observations provide some of the strongest evidence that a supermassive black hole truly exists at the center of our galaxy. No other object with that mass could fit within such a small region. The motion of these stars acts like a probe. Their orbits trace the invisible gravitational landscape around the black hole. Gravity reveals the presence of something we cannot see directly. The stars behave like glowing markers moving through curved spacetime. Their motion writes a map of the invisible. Gravity can bend time so strongly near black holes that clocks slow dramatically. The stronger the gravitational field, the slower time passes relative to distant observers. Near a black hole, this effect becomes extreme. If a clock were placed close to the event horizon, it would tick much more slowly compared to a clock far away. To an outside observer, time near the black hole would appear to stretch. Processes happening there would seem to unfold in slow motion. From the perspective of someone near the black hole, however, their own clock would feel perfectly normal. This difference arises because gravity changes the geometry of spacetime itself. Time is no longer a universal rhythm shared by all observers. Instead, it becomes a local experience shaped by gravity and motion. The closer you move toward intense gravity, the more spacetime curves, and the more differently time flows compared with distant regions of the universe. Black holes, therefore, do not only trap matter and light, they also reshape the very passage of time. Accretion disks around black holes shine brighter than entire galaxies. Material falling toward a black hole rarely plunges directly inward. Instead, it spirals around the black hole, forming a rotating disk. Within this disk, particles collide constantly. Friction and compression heat the gas to extraordinary temperatures. The glowing material can radiate enormous amounts of energy. In some cases, the brightness of the accretion disk can outshine the entire galaxy surrounding it. These luminous regions are called quasars. They are among the brightest objects in the universe. The black hole itself does not emit the light. The energy comes from the gravitational energy released as matter falls inward. Gravity accelerates the material. Friction converts motion into heat. Heat produces light. As gas moves closer to the event horizon, its speed approaches a significant fraction of the speed of light. Magnetic fields within the disk can channel some of the material outward in narrow jets. These jets shoot into space at nearly light speed, stretching for thousands of light years. A black hole therefore becomes both a destroyer and a beacon. Gravity draws matter inward, yet in doing so, it can power some of the most luminous phenomena in the cosmos. Gravity can even warp the appearance of objects near a black hole. If you could observe a black hole from nearby space, the view would appear deeply distorted. Light from background stars would bend around the black hole's gravity. Some light paths would circle the black hole before escaping. This bending creates strange visual effects. Stars might appear duplicated or stretched into arcs. A dark circular shadow would mark the region where light cannot escape. Surrounding that shadow would be a glowing ring of light produced by photons traveling along curved paths. This effect is sometimes called gravitational lensing in its most extreme form. The image of the black hole becomes a warped window into the surrounding universe. Even the sky itself would appear twisted by the curvature of spacetime. Such views are not merely theoretical. In recent years, telescopes working together across the Earth have produced the first direct images of the shadows of supermassive black holes. These images confirm predictions made decades earlier. Gravity does not only control motion, it reshapes how the universe appears to anyone watching from within it. Gravity also governs the motion of entire galaxies when they collide and merge. Galaxies are not static islands in space. Over billions of years, gravity slowly pulls them toward one another. When two galaxies approach, their stars rarely collide directly because the distances between stars are enormous. Instead, gravity reshapes the galaxies themselves. Their spiral arms stretch and twist. Long streams of stars can be pulled outward, forming luminous tidal tails that extend far into intergalactic space. Gas clouds within the galaxies collide and compress. These collisions often trigger bursts of new star formation. Entire regions of the galaxies may suddenly fill with brilliant young stars. Meanwhile, the supermassive black holes at the centers of the galaxies begin to spiral toward each other. Eventually, they may merge, releasing enormous bursts of gravitational waves. The galaxies themselves slowly settle into a new structure. Two rotating disks may become a single, larger, elliptical galaxy. What appears violent in images unfolds over immense stretches of time. Millions of years pass during each stage of the process. Gravity does not hurry, yet its influence reshapes entire galaxies. Our own Milky Way is expected to collide with a neighboring Andromeda galaxy in several billion years. This future event will transform the night sky for any observers living in that distant era. The two galaxies will pass through each other repeatedly. Their shapes will stretch and distort. Eventually, they will merge into a single, larger galaxy. Stars from both systems will mingle. But even during this enormous encounter, the chance of two stars colliding directly remains extremely small. Gravity will rearrange their paths, not smash them together. From within the merging galaxies, the sky would appear extraordinary. New streams of stars would arc across the heavens. The familiar patterns of constellations would slowly dissolve. New ones would emerge. Over time, the combined system will settle into a stable structure. Astronomers sometimes call the predicted result Milkomeda. It will be a new galaxy formed from the union of two ancient star systems. Gravity will be the quiet architect guiding the transformation. Black holes merging during galaxy collisions produce some of the most powerful gravitational waves in the universe. When two supermassive black holes spiral toward each other, their enormous masses disturb spacetime profoundly. As they orbit, they emit gravitational waves that carry energy away from the system. The black holes move closer and closer. Their orbital speed increases. The waves grow stronger and stronger. Eventually, the black holes merge in a single dramatic event. The resulting gravitational wave signal spreads across the universe. These waves can travel for billions of years before reaching distant observers. Detecting them directly is extremely challenging. The distortions they create in spacetime are incredibly small. But astronomers are developing new techniques to search for these signals. By observing the precise timing of pulsars, rapidly spinning neutron stars that act like cosmic clocks, scientists hope to detect the faint ripples produced by merging supermassive black holes. If successful, this method will open a new window into the history of galaxy formation. Gravity will once again serve as a messenger, carrying information about events that occurred billions of years ago. In the far future, gravity may slowly isolate galaxies from one another as the universe expands. Today, galaxies gather in clusters and superclusters connected by the cosmic web. But the expansion of the universe is accelerating. Over extremely long timescales, distant galaxies will move farther and farther away. Eventually, galaxies outside our local group may recede beyond the distance where their light can ever reach us again. From the perspective of future astronomers living billions of years from now, the universe may appear very different. Most galaxies will have disappeared beyond the cosmic horizon. Only nearby galaxies bound together by gravity will remain visible. Gravity will keep those galaxies orbiting one another even as the rest of the universe drifts away. The night sky will grow emptier. Yet the gravitational bonds between local galaxies will endure. Gravity works locally. Even while cosmic expansion reshapes the universe on the largest scales, it holds small communities of galaxies together like islands of structure in an ever-growing sea of space. Gravity may ultimately determine the long-term fate of stars, galaxies, and even the universe itself. For centuries, people imagined gravity as something simple, the force that pulls objects toward the ground. But when we step back and look at the universe as a whole, gravity becomes something much larger. It governs the birth of stars. It shapes the evolution of galaxies. It determines how matter gathers and how cosmic structures grow. Gravity works slowly, but its patience is extraordinary. Given enough time, even the faintest gravitational attraction can reshape entire regions of space. Gas clouds collapse, stars ignite, galaxies assemble. Clusters of galaxies gather together, and over billions of years, gravity sculpts the architecture of the observable universe. Yet gravity also competes with another influence: the expansion of space itself. After the Big Bang, the universe began expanding. For a long time, astronomers wondered whether gravity might eventually slow that expansion and cause the universe to collapse again. In such a scenario, all matter would gradually fall back together in a future Big Crunch. Today, observations suggest something different. The expansion of the universe appears to be accelerating. Some unknown influence, often called dark energy, seems to be pushing space apart. Gravity continues to gather matter locally, but on the largest scales, the expansion may win. Even so, gravity will continue shaping the structures that already exist. Stars will still form inside galaxies. Galaxies will still interact and merge. Black holes will continue growing. The cosmic story remains one where gravity writes many of the most important chapters. Even if the ultimate ending of the universe remains uncertain. Gravity is not only a force of motion, it is a force of connection. Everything with mass feels the presence of everything else. The pull may be unimaginably weak across vast distances, but it never disappears completely. Every star feels the gravity of every other star. Every galaxy contributes to the gravitational landscape of the cosmos. In this sense, gravity links the entire universe together. It is a quiet conversation happening everywhere at once. Every object participates. Every particle responds. And through those countless interactions, the structure of the universe emerges. Gravity is the reason planets have surfaces where oceans can rest. It is the reason stars shine for billions of years. It is the reason galaxies hold together long enough for complexity to arise. Without gravity, the universe would remain a thin, scattered mist of particles drifting endlessly apart. With gravity, matter gathers, structure forms, and over unimaginable spans of time, complexity grows. Even life itself owes its existence to gravity's patient work. Because gravity allowed stars to ignite, stars created the heavy elements needed for planets. Planets created environments where chemistry could grow more intricate. From that long chain of events, consciousness eventually emerged. A thinking universe, one capable of wondering how gravity works. So, when we speak about gravity, we are not only talking about falling apples or orbiting moons. We are talking about the deep structure of reality. A force that quietly organizes matter across scales ranging from atoms to galaxy clusters. A force that shapes both the night sky and the ground beneath your feet. Gravity rarely announces itself dramatically in everyday life. It does not flash or roar. It does not produce sparks or explosions on its own. Instead, it operates continuously, quietly, relentlessly. Every step you take, every breath you draw, every ocean tide rising and falling. All of these movements occur within gravity's constant presence. It is the background rhythm of existence, usually invisible, yet absolutely essential. In the deepest sense, gravity is the architecture of space and time themselves. It shapes how matter moves. It bends the path of light. It slows the passage of time in strong gravitational fields. And it writes the large-scale patterns of the universe. For something so quiet, gravity has an astonishing reach. It touches everything, from the smallest grains of dust drifting through space to the largest clusters of galaxies ever observed. And despite centuries of study, gravity still holds mysteries. Physicists continue searching for a deeper theory that unites gravity with the other fundamental forces of nature. Quantum mechanics describes the microscopic world with extraordinary precision. General relativity describes gravity and spacetime on cosmic scales. But combining these two frameworks into a single unified picture remains one of the greatest challenges in modern physics. Some scientists explore ideas involving extra dimensions. Others investigate quantum properties of spacetime itself. Experiments continue. Observations grow more precise. New telescopes and detectors reveal phenomena that previous generations could never see. And through all of this work, gravity remains both familiar and mysterious. It pulls apples from trees, yet it also bends light from distant galaxies. It keeps your feet on the ground, yet it shapes the largest structures in the universe. Perhaps that is what makes gravity so beautiful. It connects the ordinary with the cosmic, the simple with the profound. A quiet force that links the everyday world with the deepest workings of the universe. And now, as the night grows calmer and your thoughts begin to slow, you might notice gravity in a new way. Not as something dramatic, but as something steady, reliable. A gentle pull anchoring you to the planet beneath you, holding oceans in their basins, guiding the moon through its silent orbit above, and shaping the distant galaxies that shimmer faintly in the darkness of space. Gravity is always there, patient, quiet, and endlessly at work. And so, as the universe continues its slow unfolding, gravity remains one of its most faithful companions. It does not rush, it does not shout. Instead, it works quietly through time, guiding matter along gentle curves through space. Stars are born because gravity gathers scattered gas. Planets form because gravity collects dust into growing worlds. Galaxies hold together because gravity binds billions of stars into shared motion. Even the vast cosmic web stretching across the universe owes its shape to gravity's patient influence. Yet gravity is never truly finished. It never stops adjusting the paths of objects. It never stops shaping the balance between motion and attraction. Every orbit you see in the sky is a conversation between gravity and movement. The moon circling Earth, the planets gliding around the sun, stars drifting through the Milky Way, galaxies slowly approaching one another across intergalactic space. All of these motions are guided by the same quiet rule. Matter curves spacetime, and curved spacetime guides motion. In our everyday lives, gravity often feels simple. It is the force that keeps our feet on the ground, the reason objects fall when we drop them, the reason rain returns to the earth instead of drifting away into the sky. But when we look deeper, gravity reveals a far richer story. It bends light. It slows time. It can trap even photons inside the darkness of a black hole. It can ripple across the universe as gravitational waves. And it can sculpt structures so vast that light itself needs millions of years to cross them. Gravity connects the familiar world to the cosmic one. The apple falling from a branch obeys the same principle that guides the motion of galaxies. The same quiet law operates across every scale, from the smallest falling pebble to the largest structures ever observed. This is one of the most beautiful ideas in science, that the universe follows patterns that remain consistent across unimaginable distances and times. Gravity reminds us that the cosmos is not chaotic noise. It is a system where simple rules can produce astonishing complexity, where patience and time can transform clouds of gas into shining stars, where the same invisible pull that anchors you to Earth also holds together the galaxy you live inside. And perhaps, in moments of quiet reflection, this idea can feel comforting. You are not separate from the universe. You are part of a vast gravitational story unfolding across billions of years. The atoms in your body were forged inside ancient stars. Those stars formed because gravity gathered matter long before Earth existed. And even now, gravity continues guiding the motion of the planet beneath you, holding oceans in place, shaping mountains and tides, keeping the moon nearby as it drifts slowly through its long orbit. Far above, stars continue their journeys around the center of the Milky Way. Beyond them, other galaxies spin slowly through space. Beyond those, clusters of galaxies drift along the vast filaments of the cosmic web. Gravity connects them all, a quiet thread woven through the fabric of reality, a gentle force that never sleeps. So as you rest tonight, gravity is still there, holding the planet beneath you, guiding the moon across the sky, keeping the sun and its planets bound together in their ancient dance. And far beyond our world, gravity continues shaping the universe in ways we are only beginning to understand. A quiet architect of stars, galaxies, and time itself. Always present, always patient, always at work. And with that thought, you can let the night grow a little quieter. Let your breathing slow. Let your thoughts drift like distant galaxies moving calmly through space. Gravity will still be here when morning arrives. Steady, silent, and endlessly shaping the universe around you. Sleep well.